everybody. My name is Yuan Deng. The topic I will share today is international problem, serialized fuzzing for ICU vulnerabilities. It's about the security of a very widely used library, ICU, which is a acronym for International Component for Unicode. I am a senior security research at financial network security level. And I am a Chrome, Apple, and Microsoft CVE hunter. My research interests mainly focus on browser fuzzing and sandbox web paths. On the right side is the logo of my company. We have a great product named Alipay or 支付宝. It's a China leading mobile payment service. You can pay for any goods on your phone. It's very easy to use. You don't have to put your big wallet into your little pocket every time you get out. You just need to take your phone. Many cities in China, like Beijing, Shanghai, or Hangzhou, people can live without cashes for months. They can buy anything use Alipay. But suddenly in Singapore, I can rarely use Alipay or any app like this. I must take my bloated wallet every time I get out. Our team, the mission of our team is to protect the security of every Alipay user. Also do security research on some popular products like Android, Chrome, Safari, and so on. The speech today mainly consists of 5 parts. First one is about ICU. I will introduce what is the ICU and how widely it is used. Second is ICU for JavaScript. I will introduce how the ICU component working with JavaScript engine. The third part is the strict filters before ICU to protect the ICU being attacked from JavaScript. The fourth part is how to fuzzing ICU vulnerabilities that can bypass all the strict filters. In the last part, I will show 3 CVEs that can work in Chrome. And one of them can work in both Chrome, Safari, and Firefox. ICU is the acronym for International Component for Unicode. It's an open source project of mature C, C++, and Java libraries for Unicode support, software internationalization, software globalization. It's widely portable to many operating systems. It gives applications the same result on all platforms and between C, C++, and Java software. The ICU project is sponsored, supported, and used by IBM, Google, Apple, Yahoo, and some other companies. This is ICU's official site. Here is some services provided by ICU. The first one is code page conversion. It's for convert text data to or from Unicode and nearly any other character set or encoding. The second one is collation. It's for comparing strings according to the convention and stands for of particular language. The third one is formatting. It's for format numbers, dates, and times and currencies according to the convention of chosen local. And there are time calculation, Unicode support, regular expression, BD and text boundaries service. There are many products and companies and organizations reported to be using ICU, like Google's Web Search, Google Plus, Chrome OS, and Android. And from Apple, there are macOS, iOS, and watchOS are also using ICU. In macOS, the library, the name of ICU library is libicu core.a.dylib, which is default contained in the macOS. From Microsoft, there are Windows 10 and Visual Studio 2017, Visual Studio Code, and Chakra Core are also using ICU. On Windows, the name of ICU library is ICUIN.dll and ICUUC.dll. There are many cars are also using ICU where the Hammer-Becker automotive system, like Alfa, Audi, Mercedes-Benz, and BMW, and Toyota, they all using ICU. Besides the Apache, IBM, Adobe, and Northrop products are also using ICU. The next part is ICU for JavaScript. In this part, I will introduce how the ICU component working with the JavaScript engine. In JavaScript, there are only a few functions that using ICU features. For example, inter.datetime format, and number format, collector, polar rules, and object.to-local string, and string to lowercase, data.to-local time string. This is the structure of V8 and ICU. When V8 executes functions that using ICU, V8 will check the arguments of JavaScript functions and only pass the nigger arguments to ICU. The filter includes JavaScript code, which in inter.js file, and CPP code in the runtime plus inter.cpp. The ICU library always split to three parts, which is libicu i18n, libicu uc, libbase i18n. This is a constructor function of number format object. There are two arguments, locals and options. The local arguments must be either a string holding BCP47 language or an array of such language tags. The NU is a unique extension key. In this constructor, only NU is allowed, which means the numbering system is to be used. The options argument must be an object with properties that were between constructors and functions. In this number format, the properties can be local matcher, style, currency, minimum integer digits, and some others. For example, we create a new number format with DE plus DE as locals, currency as style, and EUR as currency. After the format function is called, we can say the output number is in German format. German uses a comma as a decimal separator and a period for sounds. And the EUR determines the output is a Euro format. And the first line. The second output is in Japan format. Japan doesn't use a minor unit. The third output is in integer format. The number of property maximum significant digits in options is 3. So the output limits to 3 significant digits. Inter.collector is a constructor for collector as the object that enable language-sensitive string comparing. The local argument is like the number formats, except the unique extension key can be CO, or KN, or KF. The options is like the number formats too, but the properties are mostly different. The different properties are usage, sensitivity, numbering, case first. When create a new collector object with DE as a local, based on the sensitivities, the result of compare function in first line is 0. Although the two input arguments are different, but the German locals treat them as the same. But in Swedish, the output is a positive value. In Swedish, the two alpha are totally different. The inter.datetime format object is a constructor for numbers that is constructed for objects that enable language-sensitive and time formatting. The locals argument is like the number formats, except the Unicode extension key must be CA, NU, or HC. And the property of options are mostly different too. The different properties here can be time zone, R12, or weekend day. When create a new datetime format, the options can be very complex. Here the R12 is false, and the time zone is America, Los Angeles. And the other properties are numeric. The output format function is as below. It's a 24-hour time, and the time zone has been changed to Los Angeles. The output is a string. The next part is I will introduce the strict filters before ICU in V8 to protect the ICU from being attacked from JavaScript. When create a datetime format, we pass 2 arguments to the constructor, locals and options. So the first filter is for the locals. The JS function resolve local is mainly to filter the argument locals. The second filter is time zone filters. The function canonicalize time zone ID is to canonicalize the time zone as a name. The third filter is a runtime filter. The function is create datetime format with a %sign as a prefix, which means it is C++ functions that can be called from JavaScript. In the first filter, the resolve local, it calls canonicalize language tag and then remove all the extension and check the local if in array, available locals array. This array is initialized at the first and never changed. If we input invalid local, this check cannot pass, then will return false. And last, we'll check the Unicode extension with this regular expression. Then this function canonicalize language tag is complex. First, it calls is structure valid language tag. Then call function. Then our CPP runtime function canonicalize language tag is called. The first convert then local to 256 length bytes array, then convert the array to locals. If the local is invalid, this converter cannot be success. Then the function is structure valid language tag to 3 regular matches. The first regular expression is so long. It is used to match the whole local's tag string. The second language variant RE is used to match the variant part of local tag. The third language singleton RE is used to mark the extension of local tag. The function canonical time zone ID is used to filter the time zone argument. Every time zone string must be in array every location this format. The regular expression is used to match the time zone. Then the function to title case time zone location is to change the title case of time zone string. After the local option has been changed, has been filtered, they will be passed to runtime create datetime format functions, which is a CPP function, which will call the initialize datetime format function to create a simple datetime format. In the initialized datetime format, the first convert from local to ICU result bytes, then create ICU datetime format is called. And last, the create ICU datetime format function will call the create time zone function and simple date format function to create the datetime object. Next part will introduce the how to fuzzing ICU for JavaScript and bypass all the strict filters. The inter.datetime format object has 3 methods. First is the format. The second is format to paths. The third is resolve function, resolve options. We mainly focus on the first 2 functions. The format method is called. The output is a datetime string. It's a string. But when format path is called, the output is an object, which has many type properties and value properties, which contains all the datetime information. But in ICU component, they invoke the same format functions. When I start fuzz, I first think about random-based fuzz. The fuzz generated the data number, the local, and the options randomly. Then call the format functions, but the result is very bad because the most of input is invalid. Just like this as a local, there are too many filters before ICU, so the local cannot bypass all the filters. Then I tried to generate the most likely valid locals. I maintained a local array and many unique extension arrays. When I generate the tags for number format, we choose NU array. When generate for data format, we choose the CA array. So the finally language tag will be like this: tag equal to random local plus NU plus random num ID. It's like this. This is very more effective, but the randomness is reduced significantly, so we will miss some cases. Finally, I found a fuzzer in Chromium source, which use the code coverage guided nib fuzzer. But the fuzzer can only fuzz one argument. It first gets random local from array and only fuzz the data number from the data. Because the low filter is considered, the crashes cannot be triggered from JavaScript. Let's check the arguments passed from JavaScript to ICU. On the JavaScript side, there are dozens of arguments, but after the process of V8, there are only 4 arguments left to ICU. The 4 arguments only left is data, local, time zone, and skeleton. But on the JavaScript side, there will be many arguments. We start fuzz just before ICU from here. So we can consider the arguments to ICU as a class, datetime format input. This class has 4 fields: integer field named as date, 3 string field named local, time zone, and skeleton. The data of nib fuzzer is a byte stream, so we just to consider this byte stream provided by nib fuzzer is a serialized object of this object. After the serialized data stream, we can get a data format input object and pass this object to ICU. This is the way how to serialize the object into bytes. For example, this class has 2 fields, string field and integer field. When serialize the string field into bytes, the string become a non-terminated string. If the string exists, it's just append a none at the end. If the string is not exist, just put a none. The integer is serialized to a bar byte followed by the integer. If the integer exists, the bar value is true. If it not exist, the bar value is false. Because many arguments is optional. If the arguments exist or not exist, the function will jump to different branches. Then we can deserialize the object from the bytes. The data is provided from nib fuzzer. We can extract object from the string from the data bytes. After deserialize, we can get a class arguments. As for datetime format, we can serialize this object into byte string. The first is true. The integer data is serialized to true followed by data. The local is serialized to a non-terminated data string, and the others like this. But the number format is more complicated. There are many arguments passed to ICU. So the input arguments object is very big, and there are many branches. If the stack is if the stack is not exist, the serialized bytes will be like the first line. If the stack exists and the currency equal to %, the result will be like the line 2. If the state exists and currency is not equal to %, the result will be 9 3. So the fuzzer pattern is like this. First, we deserialize the input object from the data. Then pass the argument to a simple data format and create a time zone and format. And the lib fuzzer will feed back to the code coverage and getting the fuzz. This fuzz is very efficient, so we soon get tons of crashes, but most of which cannot be triggered from JavaScript. For example, this local can trigger a stack buffer overflow in ICU. But it cannot be passed from JavaScript because the V8 has many filters. This look cannot bypass the filters. The second case is auto-bound. The local is valid. The data can be valid, but the skeleton is very strange. It cannot bypass the filters. So these two cases are all invalid. We must improve the fuzzer. First, we must check for the local. We get out all the regular expressions like this. They are very, very long. First, we check the locals. And then the skeleton must be checked. Skeleton is built from the options. In options, the weekend day can be narrow, short, or long. The corresponding skeleton would be 5E or 3E or 4E, and the error year, month, day are all like this. So the failure valid bytes of skeleton can be only this string. So we must check the bytes in skeleton must be in this string. Will return false. So after the check is out, the fuzzer is more accurate. And last, I will introduce 3 vulnerabilities I hunted that work in Chrome. The first is CVE 27.15422. It's a Persian calendar integer overflow. This is a POC, POC.js. First, we create a datetime format. It's in Persian calendar. Then we change the value of function of data.prototype to a long function. This function just return without return. So every time it's called, it's just return not a number. And last, the format parts is called. The crash will be triggered. The root cause is here. It's in I18N Persian calendar.cpp. It's in this function under computer field. The 33 multiplied by data sense epoch. The data sense epoch is an integer 32. So after they multiply, the result can be overflowed to 40 bits. So the multiplied result is overflowed, and the red zero will be discarded. So the month calculated is a very big negative, and but the Persian number days array is only 12 length, 12 only has 12 numbers. So the index months will overflow very much. We access k Persian number days a month will leak the memory of the process. If x multiplied 33 is bigger than 0x8 000, the integer overflow will be triggered. So if x is bigger than 6507562, this vulnerability will be triggered. But how to exploit this? When we execute this POC, the result is below. We can get the year, the month, and a devil month. This three field, we get this three field, we can calculate the result. Then we calculate the value from leak. The Julian day is the input. The year and the day or month and the month can be leaked. So we can calculate the value leaked from the memory. This is the POC exploit executed in Chrome. We can say the logout. The left 4338350 is the index, is actually index, and the 001 is the leaked memory. We can say the leaked memory is output. This is the POC the exploit executed in Safari. The index is the same, and the leaked memory are different. And this exploit can execute in Firefox too. The index is the same, and the result are different. The patch is very simple. Just cast the days since epoch to enter 64 to avoid the integer overflow. This vulnerability is imported from October 3, 2012. It exists for more than 5 years. So any product use the ICU released in the last 5 years will be affected. This is the code git log code imported from 2012. The next CV is numbering system create instance a stack overflow. The POC is very simple. Just the locals is very long. So the root cause is here. The buffer, the stack buffer is only 19.6 now. But the after the get keyword value, the counter the counter is equal to 99. So the overflow, the stack overflow is triggered. The next is canonicalized language tag stack overflow. This is a vulnerability. Looker is very long also. The root cause is like this. For language tag, convert the ICU result, but the ICU result, you can see the local is very long, so the ICU result is very long. But this ICU result is not terminated with none. So the next stringless can be overflowed. That's all. Acknowledge to my team member Wishu and Yu Zhou and all the others. Thanks.